Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. So welcome to the online video lecture series. In this lecture, we will be discussing about autocorrelation and its properties for energy signals. So in the previous lecture, we have discussed about the properties of autocorrelation for periodic signals or power signals. Now today's class we will discuss about autocorrelation properties for energy signal. First property, autocorrelation function value at t equal to 0 is equal to the energy of the signal. Let me define autocorrelation function R of tau is equal to integral minus infinity to plus infinity x of t and x star of and x star of t plus tau dt. This is dt. Or we can say that this is minus infinity to plus infinity x of t or x star of t minus tau, either positive shift or negative shift. Now substituting this value tau equal to 0 for autocorrelation, that is r of 0 will be equal to integral minus infinity to plus infinity. This is x of t, another one is x star of t dt. So this is nothing but integral minus infinity to plus infinity x of t mod x of t whole square dt, which is nothing but energy of the signal. This is the first property. So coming to the second property, autocorrelation function exhibits conjugate symmetry. That is, r of tau is equal to r star of minus tau. So r of tau is equal to integral minus infinity to plus infinity x of t x star of t plus tau dt. Now you take complex conjugate on both sides. R star of tau is equal to integral minus infinity to plus infinity x of t. This is x star of t plus tau dt whole star. So this is equal to integral minus infinity to plus infinity x star of t and x of t as tau dt. So replacing tau with minus tau, so this shifting is minus infinity to plus infinity. This is x of t, x star of t and x of t minus tau dt. So it can be written as r star of minus tau. So autocorrelation function exhibits conjugate symmetry. And coming to the third property, autocorrelation function value at origin is always greater than or equal to autocorrelation function for all values of tau. Let us consider a signal. Let us consider a signal f of t plus f of t plus tau, or you can say minus also. So this is we are considering. We are calculating the energy of this particular signal. So this is integral minus infinity to plus infinity. So I'm taking this as some integration. So f of t plus f of t plus tau. This is, let us consider plus or minus, and square of t dt. So this is equal to 1 by, not 1 by, so integral minus infinity to plus infinity, this is f square of t dt plus integral minus infinity to plus infinity f square of t plus tau, and this is plus or minus 2 into integral minus infinity to plus infinity f of t into f of t plus tau dt. This is also dt. So here this value is nothing but energy of the signal, and similarly this is also equal to the energy of the signal. The shifted version of the signal will not change the energy of the signal. So, and this is nothing but autocorrelation of the function R of tau. So, combining this equation, so this is E plus E, and this is minus of 2 into R of tau. So, this is minus or plus. So, this is nothing but 2E minus of 2 into R of tau. So this value is always greater than or equal to 0 because we are considering the square of the signal. So E is greater than or equal to R of tau. According to the first property, energy of the signal is nothing but R of tau value at tau equal to 0. This is always greater than or equal to R of tau for all values of tau. So fourth property, autocorrelation function and its energy spectral density forms a Fourier transform pair. So you take equation for autocorrelation function, which is equal to integral minus infinity to plus infinity x of t x of t plus tau dt. So you can say star. Now Fourier transform of autocorrelation function is equal to integral minus infinity to plus infinity r of tau e power minus j omega tau theta. Now substituting this equation here, minus infinity to plus infinity, so integral minus infinity to plus infinity x of t x star of t plus tau into e power d tau replacing this value dt, this is dt into e power minus j omega tau d tau. So if you simplify this equation, so integral minus infinity to plus infinity. So before getting to this, what we have to do is just we will assume t plus tau is equal to some L, and tau is equal to L minus t. So substitute in this equation, integration. So minus infinity to plus infinity, minus infinity to plus infinity. This is x of t, and another one is x star of L is dt, and this is e power minus j omega. What is tau? This is L minus tau. So tau is nothing but L minus t. This is L minus t. This is L minus t. So this is L minus, this is t, into d tau. D tau is nothing but df. So d tau is nothing but df. Now we're making use of this. So integral minus infinity to plus infinity x of t e power minus j answer plus j omega t dt integral minus infinity to plus infinity x star of L e power minus j omega L and df. By considering this, this can be written as x of j omega into x star of j omega, or we can say that x of minus j omega into x of j omega. So this is nothing but x of j omega square. So now this is nothing but energy spectral density of the energy signal, which is generally represented as psi of omega. Now the autocorrelation function and its energy spectral density forms a Fourier transform pair.